Okay, let's unpack this. Welcome to the deep dive. This is where we grab, a stack of source material, really dig in, and pull out those core insights.
Yeah, those aha moments, the key facts that help you get informed quickly and, crucially, help it all stick. We want you to really remember this stuff.
Think of us as your guides, basically. We help you spot the patterns, understand the big ideas, see why they matter. The goal is understanding that lasts, maybe even a lifetime.
And today, we are diving headfirst into something really foundational in computer science, but also way beyond graphs.
Right, and not the bar charts or line graphs you might see in a report. We're talking about the kind that map out connections between things, complex networks.
hmm Our source material for this deep dive is mainly built around excerpts from 9.1 Graph Hello Algo.
So our mission today,
Hmm.
to really get a handle on what graphs are, look at the different types, get the language right, figure out how computers actually represent them.
And see where they pop up in the real world, because they are absolutely everywhere. We want to connect all those dots for you.
Exactly, get that deep understanding. Because graphs, they're often seen as maybe a step up in complexity from things like linked lists or trees.
That's a good way to put it. They offer a lot more freedom in how you represent relationships, which makes them super powerful, but also means there's a bit more to grasp initially.
Okay, so to build that solid foundation, that lasting understanding, let's start right at the beginning. What exactly is a graph, fundamentally?
Well, at its core, a graph is a nonlinear way to organize data. It's basically made up of just two things. You've got a set of vertices.
Vertices, okay. Points or nodes, you could call them.
Exactly, points or nodes. And then you have a collection of edges. And the edges are simply the connections, the lines between those points or vertices.
So if we imagine, say, 5 points labeled 1, 2, 3, 4, 5, the vertices.
Right.
And maybe point 1 connects to 2, 3, and 5. Then point 2 connects to 3, 4, and 5. Point 4 connects to 5 as well. Those connections are the edges.
Precisely. The graph, often written as G, is just that whole set. The vertices, V, and the edges. E. G, G, V, E.
Okay. And you mentioned linked lists earlier.
Yeah.
How does this relate? Because a linked list has nodes and pointers, right?
It does, and you can think of the nodes in a list as vertices and the pointers or references as edges. In that sense, yeah, graphs are kind of an extension or generalization of linked lists.
A very simple graph, maybe, like a straight line.
Sort of, yeah. But here's where it gets really interesting, the core difference. Linked lists are linear, right? One thing after another.
Mm-hmm.
Trees are more hierarchical. Think parent-child relationships, branching structures like a file system.
Okay.
Graphs. Graphs model network relationships, complex, interconnected webs. That's their power. Because an edge can potentially connect any vertex to any other vertex. There's way more flexibility.
More freedom than just next item or child item.
Exactly. And that freedom is why they can model such incredibly complex real-world things.
Which makes sense why there isn't just one type of graph, right?
Yeah.
The source breaks them down based on different characteristics. What's the first division?
The first big way to categorize them is based on edge direction. Do the connections have a specific direction, or are they two-way?
Okay.
So first, you have undirected graphs. Here, the edges are like two-way streets. If A is connected to B, then B is automatically connected to A. The connection is mutual.
Like being friends on Facebook, maybe? If I friend you, you friended me. It goes both ways.
That's the classic example, yes.
So the opposite must be.
Directed graphs, or sometimes called digraphs. Here, edges are one-way streets. An edge from A to B is totally separate from an edge potentially going from B to A. They might both exist, or only one, or neither.
Ah, like following someone on Instagram or TikTok. I can follow someone, but they don't have to follow me back. The edge points from me to them.
Precisely. That follow-followed relationship is a perfect example of a directed edge.
Okay, directed versus undirected. What's another way to classify them?
Connectivity is another key aspect. Is the graph all one piece, or is it fragmented?
Makes sense.
A connected graph is one where you can start at any vertex, any point, and find a path along the edges to reach any other vertex in the graph. It's all interconnected. No isolated parts.
Got it. And the alternative.
A disconnected graph. This means the graph is basically made up of two or more separate chunks or components. There's at least one vertex you simply can't reach if you start from certain other vertices because there's no path of edges linking those components together.
Like separate islands of points.
Exactly. And then there's one more variation the source mentions, adding weights.
Weights, like making some connections heavier than others.
Kind of, yeah. In weighted graphs, each edge has a numerical value assigned to it. Call its weight. This weight can represent all sorts of things depending on the context.
Like what?
Well, the source gives an interesting social media example. Imagine mapping interactions, likes, comments, shares between users. The users are vertices. An edge means interaction. The weight on that edge could represent the strength or frequency of interaction. Maybe a higher weight means you interact with that person a lot more. It adds a quantitative layer.
Ah, I see. So it's not just if there's a connection, but how strong or how costly or how long that connection is.
Exactly. Distance on a map, cost of a flight, time taken on a subway line, capacity of a pipe, tons of applications for weights.
Okay, that clarifies the main types. So we've got the basic definition, the different flavors. Now, terminology, we need to speak the language, right? What are the key terms?
Absolutely. First one is adjacency. It's simple. Two vertices are adjacent if there's a single edge directly kissing them.
So in that first example graph we talked about with points 1 to 5, vertex 1 was connected to 2, 3, and 5. So 2, 3, and 5 are adjacent to 1.
Precisely. They're its direct neighbors.
Got it. What else?
Path. A path is just a sequence of edges you follow to get from one vertex to another. It might involve going through several intermediate vertices.
So back to that example again, getting from vertex 1 to vertex 4. We said one way was 1 to 5, then 5 to 2, then 2 to 4. That sequence, 1, 5, 2, 4, that's a path.
Yep, that's a valid path from 1 to 4. There might be other paths too, of course.
Okay. Adjacency, path.
Yeah.
Right. What about how many connections a point has?
That's called the degree of a vertex. It's simply the number of edges connected to it.
Just count the lines touching it.
Pretty much. For undirected graphs, yes. For directed graph, though, we usually need to be a bit more specific because the direction matters.
Oh, right. One-way streets.
Exactly.
Yeah.
So for a vertex in a directed graph, we talk about its in degree, that's the number of edges pointing into it, arriving at it.
Okay.
And its out degree, that's the number of edges pointing away from it, originating from it.
In degree, out degree. Makes sense for directed graphs. Okay, so we know what they are, the types, the lingo. Now, the practical side, how do we actually, represent these things in a computer program?
Right, because just drawing it isn't enough if you want to compute things. The source highlights the two most common methods, the adjacency matrix and the adjacency lists.
Matrix and list. Okay, let's start with the matrix. How does that work? Let's maybe stick with an undirected graph first. Might be simpler.
Good idea. So for an adjacency matrix, if your graph has n vertices, you create a square grid, an n by n matrix. Think of it like a table or spreadsheet.
Rows and columns, both representing the vertices.
Exactly. You label the rows 1 to n and the columns 1 to n, representing your vertices v1 through vn.
Okay, and what goes in the cells?
The value in the cell at, say, row I and column j tells you if there's an edge between vertex I and vertex j. Typically, if there's an edge, you put a 1 in the cell my. If there's no edge, you put a 0.
Simple enough. 1 for edge, 0 for no edge. What about weighted graphs?
For weighted graphs, instead of a 1, you'd store the actual weight of the edge in the cell my mod j. If there's no edge, you might use 0 or sometimes infinity or some special marker depending on the algorithm you're using.
And since we're talking undirected graphs first, the connection goes both ways. How does that show up in the matrix?
It means the matrix will be symmetric. The value at my j will always be the same as the value at mj. The top right triangle mirrors the bottom left triangle.
Oh, makes sense. And the diagonal, I.
Usually that's 0 or just ignored. Most standard graph definitions don't allow edges connecting a vertex directly to itself. Self-loops, though some variations do. But for the basic matrix, the diagonal isn't usually meaningful.
Okay, so what's good about this matrix approach? What are the pros?
Speed. It's incredibly fast to check if an edge exists between any two vertices, say I and j. You just look up the value at my. Takes the same amount of time no matter how big the graph is.
Constant time, right? 01.
Exactly. Adding an edge, deleting an edge, updating a weight, also 01. Very efficient for those operations.
Sounds great. What's the catch? There's always a catch.
Space. The matrix is always n by n. You need space proportional to the square of the number of vertices, O(n).
Even if there aren't many edges.
Yes. Imagine a graph with, say, 10,000 vertices, but only maybe 20,000 edges. That's relatively few connections per vertex. We call that a sparse graph.
Okay.
The matrix still needs 10,000. 10,000 equals 100 million entries, most of which will be 0, representing non-existent edges. It can be very wasteful in terms of memory for sparse graphs.
Ah, okay. Huge space cost if the graph isn't dense, meaning lots of connections. So that must be where the other method comes in, the adjacency list.
Precisely. The adjacency list tackles that space inefficiency problem. Instead of one giant grid, you use a collection of lists, usually one list for each vertex.
So if I have vertex I, There's a list associated just with I.
Right. And that list simply contains all the vertices that are adjacent to vertex i's. It only stores the actual connections that exist.
So for our early example, vertex 1 was connected to 2, 3, and 5. Its list would just contain pointers or references to vertices 2, 3, and 5.
Exactly. No storing zeros for connections that aren't there.
That sounds much better for space, especially for those sparse graphs.
It is. The total space required is proportional to the number of vertices plus the number of edges, OV plus E, which is typically much, much less than OV2 for sparse graphs.
Okay, space efficiency is the big win. What's the trade-off then? Speed, again?
Usually, yes, for some operations. Checking if an edge exists between vertex I and vertex J is not necessarily O1 anymore.
Why not?
Because you first have to find the list associated with vertex I, then you have to search through that list to see if J is present.
And if vertex I is connected to lots of other vertices, that list could be long.
It could be. In the worst case, searching a simple linked list takes time proportional to the length of the list, which could be up to ON if one vertex is connected to almost all others. So edge lookup can be slower than the matrix's O1.
So matrix is fast lookup, potentially high space cost. List is space efficient, potentially slower lookup.
That's the basic trade-off. But the source makes a really interesting point about optimizing the adjacency list. It compares the structure having lists attached to each main entry, the vertex, to something you see in hash tables.
Hash tables. Oh, right. When multiple keys hash to the same spot, you sometimes use a linked list there. Chaining.
Exactly. And just like you can optimize that chaining in hash tables, you can optimize the lists used in an adjacency list representation.
How? What could you use instead of just a simple linked list for the neighbors?
Well, instead of a list that requires linear searching, you could store the neighbors for each vertex in a more efficient data structure. For example, a balanced binary search tree, like an AVL tree or a red-black tree.
Okay. What would that buy you?
Searching in a balanced tree is much faster than searching a list. It's logarithmic time, O log k, where k is the number of neighbors, the degree of the vertex. So edge lookup becomes O log degree instead of O degree.
Better than potentially ON, especially if degrees are large. What else?
You could even use a hash table for each vertex's neighbor list.
A hash table within the adjacency list structure.
Yeah. If you use a hash table to store the neighbors of vertex I, then checking if Jack J is a neighbor could potentially become average case O1 time again, just like the matrix.
Wow. So you could potentially get the O1 lookup speed of the matrix and the OV plus E space efficiency of the list, at least on average.
Pretty much, yeah. It adds a bit of complexity, but it shows how you can blend these ideas. The choice really depends on the specific graph. Is it sparse or dense? And the operations you need to perform most often. Adding edges, deleting, just looking them up.
That's a fantastic point. It's about understanding the tools and the trade-offs to pick the right approach for your specific problem.
Absolutely.
Okay, so we've journeyed from definition through types, terminology, and now representation with matrices and lists, and even optimization. But let's bring it back. Why does all this intricate stuff matter? Where do we see graphs making a difference out there in the world?
Right, let's connect it to reality. The source gives some great everyday examples. Think about social networks.
Facebook, Instagram, LinkedIn.
All of them. Users are the vertices. The edges represent relationships, friends, follows, connections. So, recommending people you might know. That often involves looking at paths in the graph, friends of friends, figuring out who's influential. That might relate to the degree of a vertex, how many connections they have. It's all graph analysis.
Makes sense.
Transportation networks, huge application. Subway systems, bus routes, road networks.
Right. Stations or intersections or vertices.
Exactly. And the tracks or roads connecting them are the edges. And critically, these are usually weighted edges.
Weighted by travel time, distance, cost.
Any of those, yeah. So when your map app finds you the shortest or fastest route,
It's solving a shortest path problem on a weighted graph.
bingo. Using algorithms like Dijkstra's or A that operate directly on that graph representation, it's fundamental to navigation.
Cool. Any more surprising examples?
Well, the source even mentions the solar system.
The planets and stars. How is that a graph?
Think of the celestial bodies, planets, sun, moons, asteroids as vertices. The edges could represent the gravitational forces between them. Now, obviously, the physics is incredibly complex, but modeling the system of interactions, understanding how these bodies influence each other's orbits and movements, relies on thinking about them as an interconnected network. A graph structure helps conceptualize and compute those gravitational interactions.
Wow. So from friends online to getting across town to planetary orbits, graphs are kind of a universal language for describing connections.
They really are. They provide this powerful, flexible framework for modeling and analyzing systems where the relationships between components are the key thing to understand.
Okay, that really drives it home. So let's sort of recap this whole deep dive. We started right at the beginning, defining a graph simply as points and connections, vertices and edges.
Yep. Then we looked at the variations, directed versus undirected edges, whether the whole thing is connected or in pieces, and the idea of adding weights to those edges to represent more information.
We got the essential vocabulary and adjacency for direct neighbors, path for getting from A to B, and degree for how many connections a vertex has, remembering in degree and out degree for directed graphs.
And then the big one, representation. The adjacency matrix, fast lookups, potentially high space cost, and the adjacency list space efficient, especially for sparse graphs, but potentially slower lookups unless you optimize it using things like trees or hash tables. Understanding the trade-off is key.
Right, and finally, we saw how this isn't just theory. Graphs are behind social recommendations, map navigation, even understanding cosmic interactions. They model the real world's interconnectedness.
I think the main takeaway, the thing to really hold on to, is just how versatile graphs are. They let us model complex networks in a way that simpler structures like lists or trees just can't. And knowing how to represent them efficiently, considering those space-time trade-offs, is crucial for actually using them.
Hopefully this whole discussion helps you, the listener, see graphs not just as, some abstract concept, but as a really fundamental tool for thinking about connections everywhere, giving you that understanding that hopefully lasts.
We've seen graphs model social ties, city layouts, even planetary systems. Which leads to a final thought, maybe something for you to ponder. Think about the complex systems or networks in your own life or your work. What else could you maybe model as a graph? What kinds of relationships, what kinds of connections, and if you did, what new insights or understanding might that unlock for you?